For the last century, we've mapped the observable universe in detail. We trace ancient light, weigh distant galaxies, and track the expansion of space. This chart shows how that model actually breaks down. Everything we can see and touch, stars, planets, and even our own bodies, makes up less than 5% of the cosmos. To make the math work, physicists have to plug in specific, arbitrary values for invisible forces, roughly 68.9% dark energy, and about 5.3 times more dark matter than regular matter. These numbers have long been treated as cosmic accidents. There is no underlying theory in standard physics that explains why dark energy is 68.9% rather than any other value. We have spent decades building massive underground detectors to capture a single physical particle of dark matter, with zero results. This suggests the flaw isn't in our detection equipment, but in our assumption that these forces are made of physical matter at all. We might need to stop searching for invisible stuff filling the vacuum and ask if these percentages are actually rigid mathematical rules dictated by the shape of the universe. In April 2026, researcher Nadav Bashan published a paper that approaches the problem from this perspective. He calls it the Horizon Boundary Framework. This framework moves away from particle physics and organizes the universe through three mathematical layers: a core cosmological sector, a holographic closure, and a set of geometric extensions. This approach treats the universe as a geometric object. From this perspective, dark energy and dark matter are not substances, but structural requirements of spacetime. Bashan's central equation connects the universe's expansion rate and horizon radius to the constant pi. This geometric rule provides a formula for dark energy density: pi cubed divided by 45. Pi cubed divided by 45 equals 0.689. That perfectly matches the 68.9% dark energy density astronomers have measured for years. Applied to dark matter, the equations dictate the ratio of dark to regular matter is exactly 2 pi minus 1. That result is 5.28, aligning perfectly with observed cosmological measurements. These derivations remove the need to use arbitrary estimates in our models. The math provides the numbers. These precise alignments suggest that the parameters of our universe are determined by its geometry rather than random chance. The mechanism that makes these exact numbers possible is a concept called holographic closure. At the absolute edge of our observable universe lies the cosmological horizon. This framework treats that horizon as a physical boundary layer. Consider how a sphere works. The two-dimensional surface area of its outer shell locks in the maximum three-dimensional volume it can hold. The boundary defines the properties of the interior. Holographic closure applies this to the entire cosmos. The geometry of the universe's outer edge effectively writes the physical rules for everything inside of it. For decades, we have looked for the building blocks of reality by searching for smaller and smaller particles. Bashan's framework suggests we should instead be looking at the large-scale geometry of spacetime. Searching for dark matter as a physical substance may be like looking for a particle of pi inside a drawing of a circle. Pi is not a hidden object. It is an inherent property of the circle's shape. If this framework is correct, dark energy and dark matter are simply geometric properties that the universe must possess by definition. Because this framework relies on explicit mathematical dependencies between its layers, it can be tested and proven wrong. Instruments like the James Webb Space Telescope are currently providing the most precise measurements of the universe's expansion rate in history. If future data deviates even slightly from the specific value of pi cubed divided by 45, Bashan's framework fails. If the math holds, we are living in a universe where expansion, matter, and energy are all components of a single, consistent geometric structure.